So I want to tell you about the moment distribution method. This is a simple example I made up. I've got this beam that's fixed at A and D, and I've got a roller in the middle. Okay, it says analyze the beam. That just means find the external reactions. Flexural rigidity, EI, is a constant. So I've got a distributed load, 2 kilonewton per meters between A and B. A point load at C of 5 kilonewtons. A kilonewton is about 225 pounds. Okay, and you'll notice that I've got moment reactions at A and at D. I would also have horizontal reactions. I don't bother showing them because there are no horizontal forces. So let's just say that the horizontal reactions at A and D are 0, so that's a moot point. So can I solve this using the techniques that I learned in statics? I don't think so. I think there's too many unknowns. So what do I do about this? Well, I'll use the moment distribution method. So how do I do that? There's a couple steps I want to go through to demonstrate this. Well, step 1 is to draw the free body diagram, FBD, free body diagram. That's what I did here. Okay, so the free body diagram is done. Okay, so what's the second step? Distribution factor is at the joint that rotates. Okay, what joint rotates? Joint B rotates. A and D are embedded in the wall. So it's actually B that's rotating here. So distribution factors at the joint that rotates. Okay, so what does K refer to? Okay, well that's the stiffness factor. So stiffness factor in member AB, I divided by the length of that member. Okay, the length is 5 meters, remember that? AB, 5 meters. K sub BD, the stiffness factor for BD, moment of inertia divided by the length of that segment. BD, that's 4 meters. 4 meters, you hear? So I over 4. The summation of those two, sigma K, that means I'm adding them together. 1/5 I plus 1/4 I is 9/20 I. Okay, so that's the sigma K part. Step 2, I really have two sub-steps. So the first sub-step is to find the stiffness factors. And now the second sub-step is to find the distribution factors. Okay, so the distribution factors, DF, that's distribution factor. BA, that's K sub AB divided by the summation of the Ks. So the distribution factor that starts at B, the order of the subscripts is relevant here. For the Ks, I don't care about the order of the subscripts, but for the distribution factors, the order of the subscripts are important because this means that it starts at B and it goes towards A. So the distribution factor from B to A. So dear friends, that'd be K sub AB divided by the summation of the Ks. That'd be 4/9, or as a decimal, that's 0.4 with a repeater bar above the 4. And then the distribution factor from B to D, Bravo to delta. Okay, that'd be K sub Bravo delta divided by sigma K. So that's 1/4 divided by 9/20. Obviously the i's cancel. So that's 5/9. Okay, how does that look? Okay, what's step 3? Okay, step 3, the fixed end moments. That's FEM, fixed end moment. So the fixed end moments, you can find these in the appendix of any Introduction to Structural Analysis textbook. If I have a beam that's fixed at both ends with a distributed load like this, the moment reactions at each end is WL squared over 12. Find that in the appendix of your book. Okay, a second formula that you might find. If there's a point load mid-span, then the moments at each end would be PL over 8. Okay, what does that have to do with this problem? So after looking in the appendix of my book, I'm calling this A and this B. Why? Because let's just say that B is fixed. Let's pretend that the wall, instead of being at D, it's at B. So I've got a wall here. If the wall were here, what would M sub A be? And what would M sub B be if the wall was at B? Okay, so model this part. You're looking for a pencil. This part between the pencils. Model this as though it were fixed at both ends. And to tell me what the end moments are. Okay, so I'm going to move this blue envelope here and you'll see what I calculated. Okay, so can you see this? Okay, I think that's the whole thing. You can see it now. Okay, so the fixed end moment AB from A to B. Okay, how am I calculating it? Negative WL squared over 12. That's the formula that came here. Okay, WL squared over 12. At this side, positive WL squared over 12. The W in this case is 2, remember that? The distributed load between A and B is 2 kilonewtons per meter. The length is 5 meters, so W2L5. So WL squared over 12. Can you see this? Well, answer me. WL squared over 12, I get 25/6 kilonewton times meters, or about 4.17. For both ends, just one of them is positive and one of them is negative. So those are my fixed end moments from A to B and from B to A. Okay, now do the same thing for this second scenario. Okay, so you can pull this from the appendix of your textbook. Okay, so now I'm modeling this part between B and D. Imagine a wall at B, a wall at B, and a wall at D. And I've got that load of 5 kilonewtons, which will be like P in this case. So P will be 5, L will be 4. 2 plus 2 is 4, the distance between B and D. So L is 4 meters, and then P is 5. The end moment's PL over 8. So what did I do here? So the fixed end moment from B to D, that's this one, negative PL over 8. That'll be 5 times 4 over 8, so that's negative 2.5 kilonewton meters. And from D to B, same thing, but opposite sign. 5 halves. If you want to write that as a fraction, it would be 5 over 2. I guess I'm being a little inconsistent here. Here I'm using fractions, here I'm using decimals. But the fixed end moments for this second case, 2.5 kilonewton times meters. Okay, what does this have to do with anything? Okay, I'm going to organize all this into a chart. Okay, draw the beam again like this. Notice I took off all the loads, so remember when I started this, I had this beam with all the loads. Take off the loads and you'll have this. Okay, so what were the distribution factors? Remember step 2? So distribution factors from B to A, 4/9, from B to C, 5/9. So 4/9. Where do I put that 4/9? Where does this go? 4/9, where does that go? From B to A, so up here at the top, put a 4/9, and then kind of put a box around it like so. Okay, 4/9. Okay, and then remember the distribution factor from B to D. What is that, 5/9? 5/9, where does that go? So 5/9, put that on this side. Okay, how does that look? Okay, so that's what I'll start off with. Can you see that? What are those fixed end moments that I just calculated? Remember these? Okay, so from A to B, okay, fixed end moment A to B, negative 25/6. So where do I put that? Negative 25/6. Put that right here. Negative 25 over 6. Okay, and then from B to A, that was positive 25/6. So put that over here. 25/6. Okay, what is that? All right, how does that look? What? Okay, now what is the fixed end moment from B to D? B to D, that was negative 2.5. That's 5 over 2. I think I'm going to write the fractional version here because I'm kind of inconsistent here. Okay, so negative 5 over 2, and then from D to B, 5 over 2. Okay, so let me write those on here. Fixed end moment B to D, negative 5 over 2. Okay, and then D to B, 5 over 2. Okay, how was that? Okay, so you see where I'm getting all these numbers, and you see how I'm arranging them? Okay, so off to the side here, I'm going to put F, E, M. Those are the fixed end moments. And what did I put up at the top? Were those the distribution factors? So up at the top, I'll put DF, distribution factors. So the distribution factors refer to those. Fixed end moment refers to these numbers. Okay, how does that look? Okay, so far so good. Okay, now if you're writing this down, put this off to the side because I'm going to add more information to it in just a moment. So now we have an unbalanced moment at B, step 4, the unbalanced moment at B. Okay, so what's going on at B? I've got on this side 25/6, on this side negative 5 halves. I'm going to add those two. So 25/6 plus negative 5 halves, that's 5/3. Okay, so what does that have to do with anything? Okay, that 5/3, okay, remember the distribution factor is 4/9 and 5/9? Okay, watch this. Okay, so I'm going to move this pink paper. Relax the joint. Relax the joint, some books say unlock the joint. And find the DEM. That's distributed end moment. Distributed end moment. Okay, so that 5/3 number that I found in step 4, hang on to that number. Okay, the distributed end moment for BA is negative 5/3. So I'm using the opposite sign. So here I had positive. Use the opposite sign here. Negative 5/3 times the distribution factor 4/9. So I'm talking about BA. B to A, distribution factor 4/9. Distribution factor 4/9. 5/3, that's the unbalanced moment. Opposite sign. 5/3 times 4/9. Negative 20/27. Okay, where do I put that? Negative 20/27. Okay, watch this. So that negative 20/27. Okay, so I'm going to put that right here below the 25/6. Okay, negative 20/27. Okay, how is that? Okay, you got that? Negative 20/27. Okay, now what am I hiding here? The distributed end moment to BD is negative 5/3. Okay, so the opposite of the unbalanced moment. Times 5/9. Where am I getting that 5/9? Did I just pull that out of the air? No, it's the distribution factor for segment BD. So unbalanced moment times distribution factor, negative 25/27. Where do I put that? Negative 25/27. Watch this. Okay, put that right here on this side. Okay, and if you're working with decimals, it might look a little neater. Okay, so what have I got here? What are these? So this row right here, this row will be the what? Distributed end moments, DEM. How does that look? You okay with that? Alrighty then, so now what I'm going to do is draw a perfectly horizontal line below like this. Okay, how does that look? Okay, you got it all? Okay, so I'm going to come back to this in just a minute. Okay, step 6. Carryover moment, what am I talking about? C is equal to 1/2 for this example. So the carryover moment is equal to 1/2 of the distributed end moment that I'm sending to the other side. Okay, what do I mean by that? Okay, watch this. Okay, so remember, this is step 6. I'm taking half the distributed end moments. Okay, so watch this. All right, what is half? What is half of 25/27? Because I'm going to send that over to ND. So draw this arrow. Half of this, take it over here. That'll be negative 25/54. Okay, I know these are turning out to be weird fractions, but this is an example I just made up, so the numbers might not come out very nice. Okay, so this is the carryover moment. I'm going to say COM, carryover moment. So multiply this by 1/2, and you get this right here. Okay, similarly on the other side, 27th, take that over here to A is an alpha. Okay, what is half of 20/27? I think that's 10/27. Okay, so over here, negative 10/27. Okay, how does that look? Did I line these up right? Okay, I think so. All right, how does that look? Everything good there? Okay, so what am I doing here? What step was that? Okay, that was step 6, I think. Carryover moment, that's what I just did. Half of the distributed end moment sent to the other side. Step 7, relock the joint and proceed to the next joint. Not applicable in this case. NA, that means not applicable. Not applicable in this particular example. Okay, the next thing I'm going to do, and what is the next thing I'm going to do? Okay, watch this. Okay, I'm going to draw a perfectly horizontal line here. Okay, so horizontal line here, and then here, and then here. Okay, so the very next line, I'm going to call this step 8, is to find the summation of all these columns. So sigma is equal to, find the summation of all these columns, like this, okay, so I find the summation of this column, summation of this column, summation of this column, summation of this column. Okay, so that's the solution I'm looking for. Clockwise is positive, or I should say positive is clockwise. Negative is counterclockwise. Okay, what am I doing with all this? Cut the beam into segments and put the moments that you just found. Okay, take a look at this here. Now there was AB. I cut it at B, you'll notice. So AB, I'm analyzing that segment here. And then at B, there's a little tiny piece of the beam there. And then from B to D right here. Okay, remember that 245 over 54? That's this. Do you remember the 185 over 54 on both sides of B? That'd be this and this. And then remember the 5527? Remember that? Put that here. Okay, now what can I get from this? Equal and opposite. Okay, so at B, this little tiny piece of the beam that's at B. Okay, I've got it going, what is this, clockwise? Clockwise here. So it's going to go counterclockwise here. Okay, so that's also 185 over 54. And then what? And then here I've got 185 over 54. Or for segment BD, it looks like it's going counterclockwise. So here I'll have it going clockwise. Okay, what other reactions do I have here? What are the reactions? So there was a reaction at A and a reaction at D, vertical reactions, right? Okay, there were moment reactions. I got those covered. Okay, now look at this. At A, I've got R sub A. At B, I've got R sub B. Here's R sub B. But that R sub B, part of it is coming from the left, so I say R sub BL. Subscript L means from the left. Part of it is from the right, so R sub BR, the subscript R means from the right. So actually what's going to happen here is if I find R sub BL and I find R sub BR and I add those together, then I'll get R sub B. How does that look? And then I've got R sub C. Okay, so how in blazes do I find any of these? Okay, let me analyze AB. Okay, so cover this up. Analyze this using the equations of equilibrium, and I think you can find R sub A and R sub BL if you do that. Okay, try that. Okay, so I'm covering up the other part of the beam. So AB, I remember there was a 10 kilonewton resultant distributed load on there. I forgot to have that on there a moment ago. Okay, so remember AB now. AB, I've got a distributed load of 2 kilonewton per meter. Multiply that by 5 meters. So the resultant, 10 kilonewtons. And I didn't show it, but that acts mid-span, so 2.5 meters from either A or B. Okay, so find the sum of the moments about point A for this. So sum of the moments about point A for this beam segment. I think you can see it all here. 245 over 54, that's the moment at A, plus R sub BL times moment arm 5, that's this. Okay, minus 185 over 54, that's the moment you see at B, minus 10 times 2.5, so that's the resultant of the distributed load times the 2.5 meter moment arm, set that equal to 0. And you'll find that R sub BL, 43/9 kilonewtons, that's about 4.8 kilonewtons. I know you might be more comfortable with decimals, but I'm keeping everything really exact until the end. So R sub BL, 43/9. Okay, so where does that go? 43/9, I think I'll put that on here. So this is 43/9, and then put a box around it so that whoever is looking at it realizes that you had to come up with that later. So 43/9. So now I can find what R sub A is by taking equilibrium in the y direction. So R sub A, trying to find that, minus the 10, that's the resultant of that distributed load, plus the 43/9 that I just found. R sub A, 47/9. Okay, so this will be 47/9. Okay, how does that look? Okay, so now I've got equilibrium of AB. So now I have to do the same thing for segment BD. Okay, and I threw the load on there. Remember there was a 5 kilonewton load? I remembered to put that on there. 5 kilonewtons. So here's BD. Okay, I found these earlier, remember? So I have to find, I think you can see it now, by a similar procedure I have to find R sub, I'm going to see here, that should be a D, oops. D as in delta. So R sub D, make sure you catch that. Reaction at D, R sub D, and R sub BR, so that's the reaction at B, contribution from the right. So let me calculate these. Okay, you're analyzing segment BD. Okay, so watch this. Here it is. Okay, so the sum of the moments about point D is 0. Okay, you know where I'm getting these numbers? Negative 55/27. That's the, what is that? That's the moment at D. The moment is at this point D. Okay, plus 5 times 2, that's that 5 kilonewton load times 2 meters. Plus 185 over 54, that's the internal moment at B, or the fixed end, that's what the moment would be at point B. Minus R sub BR times 4, okay, the reaction from the right at point B, R sub BR. Okay, so I find R sub BR is 205 over 72. I'm keeping things exact here. So 205 over 72, so I'm going to put that on here. Can you see this? 205 over 72. Okay, how was that? Okay, so pay no attention to this other stuff. So now find the equilibrium in the y direction. Okay, so in the y direction, the sum of the forces in the y direction is 0. I get R sub D is 155 over 72. Okay, how is that? Okay, now the reaction at B will be the combination of these two. So if you add those two together, I believe you get 61 over 8. Okay, so here I'm going to say 61. Can you see this? No, you can't see it. 61 over 8. So that's the reaction at B. Okay, how does this look? What? Okay, so there I've got all the reactions. Or do I? Okay, I'm going to go back to my original drawing. Okay, where's my original drawing? Okay, since I have you here. Reaction at A, 47 over 9. Okay, 47 over 9. What's the decimal equivalency for that? And I'll keep the fraction. You can figure out the decimals on your own. So this is a 47 over 9er at alpha. And then at point Bravo, I've got 61 over 8. Okay, don't mistakenly use this or this. It's a combination. So at Bravo, I've got 61 over 8. So here I'll put 61 over 8. And then at Delta, I've got 155 over 72. So right here, 155 72nd. Okay, how is that? Okay, so can I go to happy hour now? Okay, I forgot to put the moments there. So what are the moments? What is it? 245 over 54, was it? 245 over 54 at A. And then at D, 55 over 27. So here I've got 55 27th. Okay, and I recommend you convert these to decimals on your own. And M sub A, 245 over 54. 245 over 54. Okay, how was that? Okay, so there you have it. Okay, I think it would probably be a good idea to convert these into decimals because it would make more practical sense. It's kind of hard to envision what 245 over 54 is. But I'll leave that up to you. So how do I check my work? Did I make a mistake somewhere? Well, I recommend that you check the equilibrium of the entire beam. Now that we know all the reactions, you can take the moments about point A, for example, the moments about point B. Make sure that everything is correct in terms of the equilibrium. So I did check that, and I think I did it correctly. So there you have it.